So we went over the basic idea of hypothesis testing and sort of how sampling distributions are created, and we sort of went through this in a very sort of we sort of just walked through it with this idea of IQ plus as the example. Again, me trying to sell you some drugs, right? So hopefully that example changed your mind from the beginning, where you're like, oh, there's no way that IQ plus works, to being, well, you know, maybe it does work. Maybe, you know, maybe this does seem like maybe there's some evidence that it is working. And that's sort of the goal of that. So what we're going to do with this particular lecture is just trying to formalize what we did in the last lecture. So we sort of just basic idea of hypothesis testing in general, and let's start to define some of the processes and make it a little bit more formalized, so you can follow steps and actually do it the same way, or you know, a similar way each time. So the first one, we're going to talk about multiple sort of hypothesis tests to begin with. A one sample, dependent samples, and an independent samples test that we're going to go through all before the midterm. So this first one is really just a rehash of the last lecture, just done in a more sort of formal way, so you can sort of get the idea of how to do the steps. Okay, so the major points here is we're going to talk about how to test a single sample hypothesis versus a population in two different ways. One, if sigma is known. So again, remember, what is sigma? Sigma is the population standard deviation. So if the population standard deviation is known, we can actually do the test in a particular way. However, the more common scenario is that the population standard deviation is unknown. All right, so we don't know what the population standard deviation is, so we have to change some things and do the steps a little differently and make some slightly different assumptions. Then we'll talk about some factors that affect these kinds of tests, and then we'll get into measuring the size of the effect, otherwise known as the effect size, and then how to compute confidence intervals around the mean as another sort of descriptive measure of sort of getting an idea of how the sample and population may overlap. All right. So there's this thing that you may have heard of or may recall from high school or at some point before today, called the central limit theorem, and it's been applied to lots of different things, and you hear about a lot of things like geometry and those kinds of places. The idea, how it applies here, is how do we know how distributions will function, how they will work based on a couple different things. So we know that the central tendency of a sampling distribution, so when we take means from the same population over and over again, how will the means behave? Well, we know what the central tendency of that will be based on the central limit theorem. Will be just it'll be really close. It's going to be similar to the population mean. So the way that we actually indicate that, where the population mean is just mu, we can indicate the mean of the sampling distribution of means as mu sub m. So this is not mu, it's not the population mean, but it's the population mean as sort of averaged through the sample means that we've taken over and over again. So mu sub m is then going to be the mean of the sampling distribution. And in terms of measuring dispersion, the standard deviation of the sampling distribution of means is called the standard error, which we actually talked about before. It's a standard, it's called SE. It also can be denoted as this sigma sub m. This is if the population sigma is known, we can actually figure out what the standard error would be using sigma, and figuring out what the standard deviation of the means would look like, what the standard error would look like based on, again, some assumptions. So we can either go through this process of sampling over and over and over again. Again, that took like 10,000 samples or something crazy. It was a large number in order to figure out what the standard error looked like, how much means would vary from one another. But because people have done this enough times, they've actually figured out there's actually a fairly simple equation to figure it out. So we define this manually when we sampled, over and over again. But we can also just calculate it. what this is saying is the standard error of the mean, standard error, can be calculated directly by simply taking the standard deviation from the population and dividing it by the square root of the n of the sample. So before, in our example before, we had our sigma, right, for our for IQ was 15, right, and mu was 100. Right, this is all based on IQ. And we took sample size 25, so our n is 25. So we can figure out that the standard error of the mean is simply 15 divided by the square root of 25. So 15 divided by 5 is 3. And 3 is the number that I figured out by doing it manually. By taking 10,000 samples size 25, I actually figured out that they vary at about a standard deviation of 3. So we had figured that out sort of manually, but I didn't have to. I could have just simply plugged in this equation and figured out that the standard error of the mean is 3 when the standard deviation of scores in the population is 15. So we can just figure it out directly, which is nice because we don't have to do that sampling process over and over again. We can simply just compute it. And this thing, this part of the square root of n thing, this has a name which I just like to share because I think it's funny. This is called the squashing factor. So basically, how much does the population standard deviation get squashed into the standard error of the mean? So the larger the samples, right, the bigger the n in each sample, the more this is going to get squashed. It's going to get smaller, right? It's going to make this smaller and smaller. That makes sense because the bigger the sample is, the sort of harder it's going to be to get it to move in one direction or another, right? So if I had said we had a sample of 1,000 people that had a mean of 106, that would have already been more impressive than having 25, because getting 1,000 people to go up 6 units seems a lot harder, a lot more difficult. So there's going to be a lot less movement the larger the sample is. So that's why the standard error of the mean gets smaller as samples get bigger. Right? And we talked about before that the shape of the sample distribution will depend on one of two things. Either if we know the original population is normally distributed, that's one way. So if the population is normal, then the sampling distribution will be normal. Or if the sample size is reasonably large, then it doesn't matter what the population looks like, the sampling distribution of the mean will be normal even if the population isn't. So most of the time we don't know what the shape of the population is, so we need to make sure that we have a reasonably sized sample, that our n is big enough. And what is big enough? That's what I mentioned before. It depends on where you read. I've seen it at 20, 25, 30. So somewhere at least 20, an n of 20 or more will get you to a reasonably sized sample so that the sampling distribution of the mean will be normal regardless of what the population looks like. So when reading problems on an exam or something like that, you need to look for one or two things. It needs to say, assume a normally distributed population. If it does, then the n of the samples doesn't matter. It's going to be normal no matter what. Or it needs to say something about the sample size. And that sample size needs to be larger than 20 in order for you to assume a normally distributed sampling distribution. If we're testing a hypothesis where the population mean is known, like it is with IQ, we know that IQ has a mean of 100 in the population, so that's something we do know. And we also know the standard deviation in the population. So we know both the mu and the sigma. Both of those things are known. So we did that last time, but we didn't really, again, formally do it. So this is called a one sample z-test. Now it's a z-test because sigma is known. We're going to do a t-test in just a bit when sigma is unknown, but when sigma is known, we can do a z-test. So it's one sample because we only took one sample size 25, and we're comparing it to a population value. So that's called the one sample z-test. So to go through the steps of how to do this, the hypothesis testing steps, we need to first state the null and alternative. Now sometimes, even though it's written out as the null first, alternative second, it's sometimes easier to state to figure out what the alternative is first. So this is a two-tailed version, which is sort of weird. It's not really probably the most accurate, but let's think about what a two-tailed would look like. So if I know the population mean is 100, and I'm testing a drug like IQ+, and all I want to know is that my sample will not be the same as the population, a two-tailed hypothesis for that would be, look, I think that my population mean, mu, will not equal 100. Right? That's the basic two-tailed hypothesis. It just doesn't equal the population value that we have, the 100, which means the opposite of that in the null is that it is equal. Right? So this one has the equal sign, this one has a range of values, not equal. So our null is that I think it's going to be the same as the population, mu equals 100. And then alternative is that it won't equal 100. So we want to know what's the probability, right, that our mean of 106, of getting a mean of 106, given that the population mean is 100. This is what we're trying to test for. What's the probability of getting a sample with a mean of 106, given, right, conditioned on having a population mean equal to 100. So we're going to use z-scores from a normal distribution. And would we expect the sample distribution to be normal? So again, what was our rules? We got to be able to, in order to assume that our sampling distribution would be normal, we got to be able to know the population is normal. So IQ scores. So IQ in general is normally distributed. Right? So right away our sample size doesn't really matter because IQ is normally distributed. You may not have known that before, but it is. Right? So IQ is normally distributed, so that's great. So we know it's normally distributed based on that. But even if we didn't know that, our n equals 25, right? So because we have an n of 25, we know it's going to be normally distributed because our sample size is big enough. Remember I said as long as it's more than 20. Again, sometimes you'll see it at 25 or 30 or bigger, but let's just keep it at, let's say 20. So if we have n equals 20, then it means having an n of 25 means we're well into sort of big enough to assume a normally distributed sampling distribution. So we're going to go through and calculate our z-test based on information that we have. All right, so we're going to say our mean was 106 minus the population mean of 100. Over, now the standard error of the mean we had figured out manually, right, as 3, but we also can figure it out by saying, all right, 15 divided by the square root of n, or by the square root of 25, equals 3. Right, so 106 minus 100 divided by 3 gives us a z-score of 2. Okay. So again, this is two-tailed. So we had talked about it before that in a two-tailed distribution, where we want there to be 2.5% there, and we want 2.5% there. But that corresponds to, we need to look up the smaller portion for 0.025. Or we can look at the mean of z, because that means this whole thing in the middle is 95%, right? Which means that this side would be 47.5, and this side would be 47.5, right? If I go down, I'm looking at the smaller portion that corresponds to 2.5%, that's 0.025. So if I keep going down here until the smaller portion gets to 0.025, right here, 0.025, oops, too hard, which corresponds to 47.5 on each side from the mean to z, and also corresponds to 97.5, sort of larger portion. That z-score is 1.96. That means that the critical values we're interested in here is 1.96 there, or negative 1.96 here. So I want to have a value that's either larger than that or smaller than that. One of those two. Now this says if z is greater than, it says plus. I don't know why it's somehow lost it should be plus or minus. So because it's a two-tailed test, we can really think, well, if my z is bigger than plus or minus, right? If the absolute value is bigger than this, okay, plus or minus 1.96, we can reject the null hypothesis. So I already explained the why 1.96. You can also think about it as if I just forget about this for a second, forget about this altogether, and just say, look, because it's two-tailed, I can say is the absolute value of my z test is greater than 1.96, I can reject. So it doesn't matter what the size is, what the sign is. All that matters is if the absolute value of z is bigger than 1.96, I'm going to reject. And I can do that because it's two-tailed. Okay. So this is, when we talk about decision rule, this is what a decision rule looks like. If my z-score is bigger than 1.96, because 1.96 is my critical value, I'm going to reject the null hypothesis. All right, so then we actually apply the rule. We did the test, so let's apply the rule. So because 2 is bigger than 1.96, we can reject the null hypothesis. So we can state that the difference is significant, and we can state that this is evidence that IQ plus raised IQ scores in this sample. All right, that's the two-tailed version, two-tailed test. So this is a two-tailed version of it, but two-tailed, again, seems kind of like a weird way of testing this. I want to know if IQ plus raises IQ, so let's, maybe we should do this as a one-tailed test. So I'm showing you the two-tailed version and a one-tailed version. You wouldn't ever do both of those things. You would decide on one or the other and do one. But just to be sort of thorough, let's talk about the both approaches. So here you have sort of an alternative to that. It's, instead of thinking about it as a two-tailed test, let's do it as a one-tailed test. So you can calculate z. Now the thing is, the calculation of z actually doesn't change. It's still going to be the same process. Take your mean of your sample minus the population mean over the standard error. Okay, that's the same. So it doesn't change. All that changes is the critical value. So if z, but now see it matters if z is positive or negative, so I can't do the absolute value anymore. It actually has to be greater than a positive 1.64. Now why 1.64? So in the same way we figured out what it would be for a two-tailed test, let's think about that for a one-tailed test. So if I have a distribution and I want all 5% to be here, right? So this is now all 5% of my alpha is in one location. That means that this smaller portion corresponds to 5%. It also means that the rest of this corresponds to 95%. So I can look up the larger portion of 95 or the small portion for 5. Either way, I need to find a z-score that corresponds to that number. I need to find, instead of 0.025, I need to find one that's 0.05. Okay, so if we look here, there's either 0.0505 or 0.0495. Neither one of those are exactly 0.05, but they're both sort of equally distant from each other. So you really could pick either one, 1.64 or 1.65. They work fairly well. If you think about let's pick the one that is that is the closest without going over, you'd pick 1.65. I think I'd pick 1.64. Actually, I don't even know. I know that the real value is halfway in between these, which is why typically you see it as 1.645. But either way, you can pick 1.64 or 1.65, and it's going to be close enough either way. So 1.64 is the number. So if my z value is larger than a positive 1.64, I'm going to reject the null hypothesis. So this is my decision rule, right? So my decision rule is I'm going to decide to reject if my z is greater than that number. Well, it's the same z, nothing's changed, it's the same test, Just so because 2 is greater than 1.64 and it's in the right direction, because here's my 1.64 here. So the value that I actually get is 2, right? It's actually larger than 1.64. It's in that 5% region. That means I can reject a null hypothesis. Again, this is evident that IQ plus raised scores. So you're probably thinking, well, it seems like the same thing. Well, again, you would have done one or the other. So when you're going to do one of these kind of tests, you're going to decide ahead of time, or as you're sort of reading through the problem, or as you're trying to get set up to do a research study, you're going to decide ahead of time whether or not you're deciding to do a one-tailed or two-tailed test. It's just that I'm doing both so that it's thorough, but you wouldn't do a two-tailed and then a one-tailed. You would just do one or the other. Okay. The good news is, either way, whichever way you decided, doesn't seem to make a difference. We actually are rejecting either way, so it doesn't seem to matter. So in the last example, in the last set of slides, we talked about computing the sampling distribution of the mean. And the results should look consistent, meaning that the results we got here, the fact that we're rejecting the null, matches the sampling distribution that we walked through and talked about. Well, it looks like our sample is in a very unusual, unlikely spot in that distribution. So that our z-test is leading us to the same conclusion we did using the sampling distribution alone from the last lecture. Right, so that's good. The results look consistent. We're coming to the same conclusions. So that's what this test does. It actually just formalizes the process of doing that without having to do all the sampling, without having to do all the stuff. It just actually takes you right to it and you're able to test it. The logic of the test here is that we're going to calculate the probability of getting this mean if the null is true. So how likely is it to get our mean given that the null is true? If the probability is small, meaning the probability is less than 0.05, we're going to reject the null, and meaning that we think our sample isn't like the rest of the distribution. It seems to be unusual, so it's more likely that IQ plus worked. If the probability is larger than 0.05, then we're going to assume that it's just part of the normal distribution, part of the sampling error, and we're going to retain the null and believe that IQ plus doesn't work. So in this case, because we figured out that like 1.64 or 1.96, those cutoff criteria represented our 5% critical values, and because our test value, our z of 2, is larger than that, it indicates that it actually is smaller than 5%. Critical value surpasses, our test value, our z value, surpasses the critical value. The critical value corresponds exactly to 5%. So because our test value is larger than that, it means it has a smaller than 5% probability, which is why we decided to reject the null. Right? So small probability leads us to rejecting the null hypothesis. All right. Just as an aside, this is just, not a lot of, super fun stories to tell in stats. So I'd like to mention this. So this is a beer and the advancement of science. So about 1901, the Guinness Brewery in Dublin, Ireland, what they're having issues with trying to keep beer consistent. So they were brewing in these large batches. They were getting their grains and other things from different sources. They're trying to figure out a way to make the outcome sort of as consistent as possible. So he was trying to be able to figure out how do they know if they get a big batch of grains of some sort, like barley or something, how are they able to figure out if the population of all that barley or grain or whatever is good without having to go through and test the whole thing? So they started doing this idea of sort of quality control by sampling parts of populations, parts of shipments of grain, let's sample parts of it and actually be able to decide whether or not there's issues with the quality of that population. Except it was sort of hard to do. How do you actually do this in a consistent way? So a man named William Gossett was working for Guinness. He was either the brewmaster or assistant brewmaster or something like that. And he started working with Carl Pearson, who again is the Pearson correlation. We'll talk about more later on. And under the guidance of that, he actually developed something called a t-distribution, which it's an adjusted distribution that adjusts for the size of the sample and some other things. And what makes this interesting is that it's not called like Gosset's t or whatever. It usually is referred to as the student's t-distribution. And the reason why is because William Gossett was working for Guinness and developing this, if he had published it, or tried to publish it, Guinness likely would have stopped him from doing so and kept it as proprietary to Guinness, the Guinness Brewery. So instead, he published it anonymously to a journal under the name just Student, and it got out there to everybody, so other people can use this sort of method to sort of adjust for sample size and other things when trying to assess samples from populations. So it has been forever known as Student's T. So he was able to do that. So the idea that sort of having beer as a driving force actually led to an advancement in how statistics were sort of used, I think is awesome. And the fact that he decided to just not necessarily screw Guinness Brewery, but to decide in favor of science as a whole, as opposed to sort of the benefit of just one brewery. He actually put it out there for everybody, which is pretty awesome too. There's a link here if you'd actually like to learn a little more about it. It's pretty interesting, so you can click here and learn a little more about this stuff. All right. With that being said, the reason why William Gossett had developed this adjusted t-distribution is because when it comes to again, when you're getting grain from a distributor or something like that, from farms or from wherever, you oftentimes don't know information about that. Like in this case, let's say you don't know what the variation is. So you don't know what the standard deviation for the population is. So you're going to have to make some assumptions and do a little bit of extra work. So let's assume our same example. So our same example we know that the population mean for IQ is 100. We can still assume that. We can still assume that our sample mean is 106. But now we don't have the population standard deviation, that sigma, we don't know. What we know instead is that our sample standard deviation is 7.78. So if I actually look at the 25 people we have, they actually have a standard deviation of 7.78. And so these are both from the sample. I don't know anything about the population except for the mean. So now we're going to have to rely on the sample standard deviation instead of the population, and that's going to change things a little bit. Okay, so we don't know sigma, but because we have a sample of size 25, we can compute S, and we can then take a guess at sigma with S, right? We can actually just use this as our best estimate of sigma. But like it says here, unless we have a large sample, S is likely to underestimate sigma. So again, think about populations are huge, samples are small, okay? So it's very unlikely that this standard deviation, right, is ever going to be the same as this standard deviation, right? It's very unlikely that we're going to get the same size standard deviation from here unless this sample is really big, like, 100, 200, 500, 1,000. Unless it's really big, it's not going to be anything close to the population. All right, so this is likely always to underestimate this. So we need a test based on the normal distribution. So I'm sorry, if we just forget about the fact that we don't know sigma and just do a z-test anyway, what's going to happen is because this ends up being too small, if we just plug this in for sigma, remember sigma was 15, right? So if I just plug this in place of this, I'm going to overestimate my test statistic over and over again. I'm going to inflate. I'm going to make more type 1 errors because I'm dividing by a much smaller number. So I can't use z anymore because z is not going to be biased. So I need to figure out a way to adjust for that and use a different distribution besides z. So if I took population that has a variance of 138.89, and I just take 10,000 samples size 5 over and over again. we see is that rarely you're going to get large variances. You're going to get some variances out here that are big, right? But the majority, most of them, the largest proportion of scores are going to actually be lower than that our 138.89 that is in the population. So with sample size 5, almost 60%, 58.94% of the variances in the sample are actually smaller than 138.89. So we're underestimating our population variance nearly 60% of the time. Now, if everything was sort of normally distributed, you'd expect it to be about 50-50. So we're just overestimating just a little bit, but still there's an overestimation. As this number gets larger, this underestimation here that we're getting is actually going to get smaller. Once you get to a large enough sample, these will start to sort of even out. You start to get about half and half. So the smaller the samples, the more sort of adjustment is needed. The bigger the samples, the less adjustment when trying to estimate the population. So since S is the best estimate of sigma that we're going to have, right? So our sample standard deviation is the best estimate of the population. It's really the only thing we have. Then we need to develop an S sub m, a standard error of the mean based on S, and that's going to be the best estimate of sigma that we're going to have. So if we use S to create a standard error, that's going to be the best estimate of the population we're going to get. Since Z does not work anymore because of this sort of bias that gets introduced, we need a different distribution. We need one that's based on S instead of sigma. We need one that adjusts for the underestimation, right? And one that takes sample size, like degrees of freedom, into account. So instead of having a single Z distribution to be able to test everything like we did when sigma was known, we now need multiple distributions for different sample sizes, and that will adjust for the underestimation of the variance and is based on the sample value instead of the population value. That distribution is known as T. So the T distribution is really an adjusted Z distribution that adjusts for the sample size and the degree of underestimation in estimating the values. It looks very much like a Z. It's the mean, median, mode are all equal to 0. So it's like a standard normal distribution. It has asymptotic tails. It's just that instead of it being one distribution, there is like an infinite number of them. Right? So there's an infinite number of T distributions you can use. At low degrees of freedom, it's very leptokurtic, meaning that it has a sort of a skinny peak with big fat tails, because the tails have been adjusted to push the critical values out a little bit farther to adjust for the underestimation of the variance. At high degrees of freedom, it becomes a lot more normal. And technically, if the degrees of freedom are infinite, if you just have an infinite number of degrees of freedom, T and Z then are about the same. Actually, they're exactly the same and infinite. So at super large degrees of freedom, there's no difference between Z and T. They become pretty much the same thing. Matter of fact, you can assume that that Z is just the T distribution at an infinite number of degrees of freedom. The reality is, though, they actually get close. T and Z become pretty close, even about 100 degrees of freedom. So if you have, 101 people in your sample, T and Z are actually already fairly close, even at 100 degrees of freedom. So once you get to a large enough sample, the adjustment starts to become much smaller. Okay? So this is what a T distribution sort of looks like, the different versions of it. So here, when the n equals 2, that's that sort of middle one here. So you get it's got a skinny little point relative to tails that are a lot fatter. Notice the curve comes up more here. So they got fatter tails. It's a skinnier distribution. As you go up in degrees of freedom, like to 30. It becomes a lot more like the normal distribution, which is the one in red at the top. So even at an n of 30, the difference between Z and T is very, very small, right? So that's the two, the black and the red sort of line going there are the 30 degrees of freedom, or the n of 30, which is really 29 degrees of freedom, and the normal distribution in red. So if you think about the reason why this works, or why this happens the way it does, I want to adjust for the fact that I want to adjust for the fact that the standard deviation in my sample is going to be smaller than the population one normally, more often than not. So because if I use my standard deviation for my sample in a sort of z-test-like equation, like the mean of my sample minus the population over a standard error based on S, I'm likely to overestimate. I'm likely to get a number that's too big, leading to more type 1 errors. So if I look at a normal distribution, let's say that this is 5%. I don't know if it is, I'm just making it up. Let's say this is 5%. Okay, that's my 5% mark. Now look at the one in light blue. To get to that same 5%, I'd have to go much farther out. This, you know, I'd have to be like here to get to the same level of 5%. Again, this is not exact, just close. Because this thing is fatter like this, it actually pushes the critical values, the cutoffs, it pushes it out farther. So my critical values are going to be bigger. I'm going to get bigger critical values with smaller n. As the n gets bigger, the critical values actually start to become closer and closer to the z critical values here. And the reason for that is it's actually making the critical values larger to make up for the fact that our test statistics are going to be larger because we're dividing by a smaller number. Where before, you know, our sigma was 15, which led to a sigma sub m of 3. Now we're talking about an s equal to 7.78. So when I divide that by the square root of 25, it's going to be a number that's much smaller than 3. So to make up for the fact that we're dividing by a smaller denominator, we need to adjust our critical values so that if our test statistic is still larger than this bigger critical value, then we can feel pretty comfortable that we can reject the null. And it's not just about the inflation around using a smaller standard deviation. So that's the process. So T actually just does that adjustment for us. It moves our critical values further out in the details. When we have a small n, as n gets larger, it moves them back in closer to z. And technically, when it gets to be infinitely large, they're exactly the same. But even as small as 30, you can see the differences between the red and the black are not very much. There's this tiny little difference between those two numbers. So as numbers get bigger, the adjustment that T does, it actually adjusts less and less. So that it's much more like the z distribution. Especially, I think when you get to 100, a sample size of 100, the differences are in like the third decimal place between z and t values. Okay, let's look at what this looks like for our example with IQ+. So degrees of freedom. So skewness of the sampling distribution of variance decreases as n increases. So I mentioned that before, that we have a very small sample. You're going to get more variances that are underestimated, which is why we're trying to adjust for that. As that n increases, it starts to sort of even out, and you're going to under and overestimate about the same amount of time. So as n increases, you need to do less adjustment. So T will differ from Z less, for the same reason. T will differ from Z less as sample size increases, because the underestimation of the population variance becomes less and less as n gets bigger. We don't need to adjust so much. So therefore we need to adjust T accordingly. So we need to figure out what the degrees of freedom are for a test, and then we're going to look up our critical values based on those degrees of freedom, which is why T is based on degrees of freedom where Z wasn't. We didn't have to worry about degrees of freedom with Z. We do now for T because there are multiple T distributions. All right, so if we go with this idea that let's forget for a second that the standard deviation in the population is 15. Let's say we don't know that, right? So we're going to assume that we don't know sigma. So this is called, if we have one sample versus a population mean like this, where sigma is unknown, this is called a one sample t-test. So you notice the null and alternative, if we're doing a two-tailed test, the null alternative are the same. We're testing the null that mu equals 100 and the alternative that mu does not equal 100. We want to know what's the probability that the mean equals 106 given that the population mean is 100. It's the same assumption, we're trying to do the same thing, it's just we're going to use a different process. So we're going to use a t-table to look up a critical value using degrees of freedom instead of using the z-table we did before. We're then going to take our t observed instead of our z test from before. We're going to compare it to our t critical, which is the one from the table. And then we're going to use that to make a decision on whether or not we think IQ plus worked or not, or whether we're going to retain the null or reject it. Okay. So it's the same exercise, same as z, same thing we did with z. It's just we don't know the sigma anymore, so we're going to replace it. So notice it's the same process. T observed, this is our t test statistic, our observed t, is the top part is the same. Our sample mean minus population mean. So this is still 106 minus 100. Instead of, before we took 15 divided by the square root of 25. Well, now we're going to take 7.78 over the square root of 25. Right? Because that's what S sub m is going to be. It's going to be our standard error based on S instead. Let's figure out what that looks like. 7.78 divided by 25. I don't know why I did that. Divided by 5 is, this ends up being 1.556. All right, so remember before, our standard error when we use 15 was 3. So this is half, right? Which makes sense because this is nearly half of the 15 units. So we got a much smaller standard error. So this is still going to be 6 divided by 1.556. 3.856. 3.856 or 3.86, something like that. Okay, so we got this 3.856, which is our t observed. So yes, this is much larger. Notice this is an inflation relative to what we know from the z value, which is that we should have divided by 3, and we got simply a z of 2. So we're getting a t of 3.856, which is a lot bigger. So we need to figure out, with alpha equal to 0.05, degrees of freedom 24, because we have 25 people, so 25 minus 1 is 24. So just to recall that, degrees of freedom here, degrees of freedom for our t-test is going to be your n minus 1, which is 25 minus 1 equals 24. So this is what a t-distribution looks like, at least the one that you have on the website. So just a couple things about how it looks. So one, it says level of significance for one-tailed test across the top. And then the next line says level of significance for two-tailed test. So it makes sense that for two-tailed, like for a 10% two-tailed test, that's going to correspond to the same point in the distribution as a one-tailed test at 0.05. So typically the values you're going to look at are for a one-tailed test at 0.05 and for a t-tailed test at 0.05, right, which corresponds to a one-tailed test at 0.025. These are the two columns you're typically going to want. For a t-tailed test, you're going to start here, and these are your values. For a one-tailed test, you're going to start here, and then these are your values. And all you got to do is look down the distribution to find the degrees of freedom. So this is my two-tailed test here. I'm going to scroll down to 24 and find my critical value here of 2.0639. So that's my critical value that I'm going to use. And if I do this as a one-tailed test, it's just one column over. Right, it's this column instead. One-tailed 0.05 is 1.7109. So just so that it's all together on the slide, I'm going to go just one slide over for a second. Of course, I got a bunch of stuff written on it. But you can see the same basic idea here, that for one-tailed 0.025 corresponds to a two-tailed 0.05, right? And then for a one-tailed 0.05 corresponds to a two-tailed 0.10. So again, it's these two that we typically want to stick to. One-tailed 0.05 is this column. two-tailed 0.05 is this column. So if I go down, two-tailed 0.05, you get to 2.064, which is the same as it was, just easier because it's on the slide. So 2.064, my critical value. 2.064 is my critical value when I'm doing a two-tailed test. Okay, 2.064. My decision rule, which I don't really have here, would be, I should say something like, if my T observed, let's say TO, is greater than, this is a two-tailed, so the absolute value, T observed, is greater than 2.064, I'm going to reject the null. Right, that's my decision rule. If T observed is greater than 2.064, I'm going to reject the null hypothesis. So then my decision, which is this, is going to be, well, okay, so I got, my T observed is 3.856. Since 3.856 is greater than 2.064, I am in fact going to reject the null. Right? So this is the two-tailed version. Let's do it again, just for the sake of completeness, as a one-tailed version. All right, it's the same process it was for the z, right? So my null is, well, look, if mu is great, so the alternative is I want mu to be greater than 100. It's a one-tailed test. So I'm testing whether or not it's actually greater than 100. I don't care if it actually is less than 100. So that means my null is just the same idea, but in reverse. So if this is, I'm testing if mu is greater than 100, then here I'm testing if mu is less than or equal to 100 as my two hypotheses. The T observed value is the same, right? The test is the same, nothing changes. I did the test here, right? And got that it was 3 over 1.556. So that T observed doesn't change, right? The only thing it changes is what we're comparing it to. So I forgot what the number was. It was 3.856. So the T observed value is the same. 3.856 doesn't change. Okay. What does change is that because we have an alpha of 0.05, degrees of freedom equals 24, I now want a one-tailed T critical. Before I was doing a two-tailed test, which is why I came to this column, my 0.05 two-tailed, and I scrolled down to 24 and I got this 2.064 number. All right, now I'm doing a one-tailed test. So I'm shifting over one column to the one-tailed 0.05 here, scrolling down to 24 here, and I'm getting that the value is 1.7109 based on the table. All right, so this is my critical value if I'm doing it as a one-tailed test. So, just to take a peek at the table on the next page here. Again, I now want the one-tailed 0.05 version, go all the way down to 24 degrees of freedom, and 1.711. So it's just, this is rounded to 3 decimals instead of 4 like the table, but same idea. So my critical value is 1.711. Yeah. And again, what I don't have, I should have written here is my decision rule, which is, if my, now it matters here because this is a one-tailed. So your decision rule should match, I shouldn't do that, it looks like I'm doing an equal sign, should match your alternative hypothesis. So if my T observed is greater than 1.711, I'm going to reject the null. Now, what if I had done this in reverse? If I was looking at something that was lowering IQ, and it was mu is less than 100, and this was mu is greater than or equal to 100, I had this reversed. Well, then this should be reversed too. T observed is less than, and this will likely be a negative number, because it's flipping into the other side of the distribution. So if that's true, make sure that your inequality here matches the inequality here, and it'll keep you from making mistakes about your decision. So, okay, So my decision rule is if my t observed is greater than 1.7101, I'm going to reject. So now I did my test, which is 3.856. That. And since that is greater than 1.711, oops, so I could draw that in a better place. Since that is greater than 1.711, I'm going to reject the null. And again, decide in favor of, it seems like IQ plus is actually raising IQ scores. Okay, so that's the one-tailed version. Again, you would do one or the other, not both. And that would depend on your hypothesis and what you're testing and whether you do a one-tailed or two-tailed test. But you wouldn't do both of them. So with n equals 25, our t observed was that 3 point, whatever I just said it was a second ago. So another way of thinking about this, just to summarize, 3.856. So with t observed with 24 degrees of freedom was 3.856, right? Yeah. Because 3.856 is larger than both 2.0, I forget what the number is, right? 2.064 and, oh, wrong one, I did it backwards. Since 3.856 is larger than both the one-tailed, which is 1.711, and the two-tailed, right, 2.064. We reject the null under both one and two-tailed hypotheses. We would do it either way. Now, you wouldn't do both. You do one or the other, but in this case, it doesn't make a difference which one you choose because you're going to come to the same conclusion, which is we're going to conclude that taking IQ plus leads to a higher IQ than normal for those 25 people. So things affecting the t-test. So factors affecting the t-test are also things that affect power. So remember, the power of a test is the likelihood that you're going to reject a false null hypothesis, right? So if your null hypothesis is false, meaning that your alternative is true, the power is the probability that you'll be able to reject the null when it's false. So what is going to actually lead to more likelihood of rejecting the null when it's false? Well, the bigger the difference between the sample and population means, the farther they are apart, the easier it's going to be, the easier it's going to see, the easier it will be to see if the two are significantly different. It's going to be a lot easier, just even by eye, that if for instance I had said that when people take IQ plus for 10 days, they end up having a mean of 115 or 130 or some ridiculously large number, you're not going to need a test to be able to know that that's a huge amount of change, okay? So the magnitude of the sample variance is also going to have an impact here. So the smaller the variance in the samples, the larger the test statistics. So if you can actually get your sample standard deviations to be small, you'll be dividing by that divided by square root of n. It's going to actually lead to larger t observes, right? So you're going to get a bigger, a more powerful test simply by having smaller variances, and then the sample size, of course, plays into effect because if you're looking at the equation for all this, where t equals the mean minus the population over s divided by the square root of n. Right, so all these things are talking about how do I make n bigger. All right, well, if I look at this, if I make this difference bigger, that's talking about the effect. Right? If I make there's a bigger effect between your sample and the population, you're going to make t larger. Okay. If the variance is smaller, the smaller the variance is, the bigger t will be. All right, so that's why the magnitude of the sample variance is going to have an impact. So if this is smaller, this is bigger. The sample size affects it because the bigger the sample size, the larger this is. All right, the bigger that is, the bigger t will be. because as n gets bigger and you're dividing by it, it's going to make the denominator smaller. As the denominator gets smaller, t is going to get bigger. Okay, so we want oftentimes bigger n. So one of the easiest ways with which to actually increase your power, increase the chances of getting a significant t-test, is to just use more people. So even if I don't change the formula for IQ plus and the effect stays the same size, I can't really do much about addressing the standard deviations or the variances amongst the people that are taking it, but I can recruit more people and have a larger sample, which in effect lead to a better chance of having a significant t. So those three things all affect power, which means they're going to affect the ability for the t-test to actually reject the null. Other things are that affect it a little more indirectly maybe is the significance level of alpha. We don't really have much control over this because, again, the assumption is that it's going to be at least 0.05 or less. So there's not really much we can do here, but actually increasing alpha does actually lead to more chances of rejecting the null and actually having significant t's, because you're actually allowing more type 1s, which means you're going to reject more often. And then, as we talked about before, one-tailed versus two-tailed tests have an impact because one-tailed tests tend to be a little bit more powerful than two-tailed tests because the critical value, when it's 5%, comes in a little bit more, or it's 2.5%, it's a little farther out. So as long as you're hypothesizing in the correct direction, a one-tailed test will likely be more powerful than a two-tailed test. So knowing that an effect is significant doesn't tell you everything you need to know. We know that the difference is significant, but it doesn't mean that it's important. I mentioned that before, that just because we know that the likelihood of it occurring by chance is small doesn't mean that it's important. So we know the population mean is 100. We know the sample mean is 106. So we know this is like a 6-point change, roughly a 6% increase relative to the population mean, right? So we were at 100. This is like a 6% increase. So it's hard to know. This is large, and most of you were likely responding to this idea when you first saw it. That this doesn't seem like a very big change. It doesn't seem like a substantial change from the population value. So we oftentimes can look at this as a raw difference, a 6-unit raw sort of effect. But it's hard to know if that's big or small. So we tend to not look at the raw effect size, but we want to look at some kind of standard effect size. So later we will develop this in more standard deviations, and we'll do more with this. But let's just look at this sort of simply. In our example, we have standard deviation of 7.78 from our sample, right? So we can look at this, instead of thinking about the standard error, we can look at this as, all right, so we had 106 minus 100 over our standard deviation is 7.78. We get 7.78. And we could think, all right, well, how many standard deviations is this? So we can think that's 6 divided by 7.78, which is 0.77. All right, so this is 0.77. So this tells me that relative to the sample standard deviation, IQ plus or whatever was able to move people's responses over 3/4 of a standard deviation, right? So 7.78 is one standard deviation. This went 77% of the way. So we got 3/4 of a standard deviation sort of movement from away from the population mean. This may not seem very large, but this whole thing, this effect size, is something known as Cohen's d, oftentimes called d hat. And Cohen, who developed this, had put together some criteria for things where a Cohen's d of 0.2 was considered small. A Cohen's d of 0.5 was considered sort of moderate, medium. And if you're at 0.8 or more, that's considered a large effect. So we're nearly at the large effect cutoff. So in standardized units, being able to move 77% of the way towards the standard deviation is actually a fairly large effect size. Because we're trying to move 25 people in a direction. It's actually a fairly large shift, in effect size. So even though this doesn't tell us if it's like, you know, the likelihood, the probability of it occurring by chance alone, this does give us an idea of like, okay, well, how big is the effect really? Okay, so let's talk about confidence intervals for a sec. So for confidence intervals are this idea that like whenever we pull a sample from a population, we get one shot at that. Like we just get one sample mean. That's it. One mean, one sample. So oftentimes people want to know, okay, well, if we were to do this again and pull, you know, samples from the population, what range of values would we get? And be able to create an interval that sort of estimates the likely values we would get from the same population. So this is when we want an interval estimation, an interval estimate. Given the sample mean, we can calculate an interval that has a probability of containing the population mean, and this can be done if we know sigma or not. Right? We can do either based on z or based on t. Doesn't make a difference. I mean, it does make a difference on how you do it, but you can do it either way. So if sigma is known, then we can use our 1.96, which corresponds to the middle 95% of the distribution. We can actually just use that, and we can figure out, we take our sample mean, and we can add and subtract that 1.96 times the standard error we get from our z-test, our one sample z-test. If sigma is unknown, right, so if we don't know sigma, then we're going to use t instead. So we're going to take our same sample mean, we're going to add and subtract. We got to look up what the two-tailed t value would look like. And this doesn't matter if you did a one-tailed t-test as your test. If you're looking at the confidence intervals, you're still going to use the two-tailed values for the confidence interval because you want the values that are equally distant above and below the mean. So you want there to be two tails, and this should correspond to 95% or the 0.05% in alpha. You're going to take your standard error that you got from your sample and use that as well. So you need to look this up in the t value and use your sample-based standard error, and you can get a confidence interval around that without knowing sigma. So let's look how that works. So here it is. If we know sigma, it's a little bit easier. So our sample mean was 106. We're going to add and subtract. Our 1.96 is standard, and that's that because that's a z-score that corresponds to the two-tailed test. So that's going to be the same. And we're going to multiply that by our standard error of 3. And standard error of 3, remember, we got from 15 divided by the square root of 25, which is 3. And that's our standard error of the mean we got when sigma was known. So 1.96 times 3. 1.96 times 3 equals 5.88. So our confidence interval is going to be 106 plus or minus 5.88. So 106 minus 5.88 equals, so we're going to say that our confidence interval is 100.12 is less than or equal to our population value. Is less than or equal to 106 plus 5.8, oops, not 5,000. 106 plus 5.88 equals 111.88. That. So this would be our confidence interval around the mean. So what this is telling us that we can be 95% confident that the population that this sample came from, remember we have a sample with a mean of 106, that the population that this sample came from likely has values that range from 100.12 to 111.88. Right, so those are the values of the real parent population of this sample. Notice that 100 is outside of this, right? So a population with a mean of 100 doesn't seem to explain our sample very well based on our confidence interval. So what if we did this instead using t? The same process, just a little bit more of a pain in the butt because we gotta look up the t values. The 1.96 is a known, so the z, this isn't. So it's going to be now 106 is the same, plus or minus. We look at the t value, the two-tailed t value. So 24 degrees of freedom. The two-tailed t value, I think is this, but let's check. 0.05, two-tailed, down to 24 is here, 2.064, I think was the number we used before. Okay. So 106 plus or minus 2.064 is our t value. Now I need to multiply that by our standard error based on the sample. So that's 7.78 divided, 7.778, I think, 7.778. So now I don't remember. Let's go back, make sure, yeah, that's just 7.78. 7.78 divided by 5, which is the square root of 25, is that 1.556 number, 1.556. If I multiply those, 2.064 times 1.556 equals 3.211, so this is basically 106 plus or minus 3.212. So if we do 106 minus 3.212, I get 102.788 is less than or equal to the population value that I'm looking for. 106 plus 3.212. 106 plus 3.212 equals 109. Less than or equal to 109.212. Okay, so what it's saying is that the 95%, based on the t, based on the fact that we had to estimate our s sub m based on t, that we're 95% likely that the values for the population with which this sample came from fall between 102.788 and 109.212. Notice that neither interval includes 100. I mentioned that before. That's the population mean of IQ. So it sort of helps us to come to a similar conclusion that if we're 95% confident that these are the ranges that the population values would look like based on the sample, the fact that 100 isn't there is why we sort of rejected it given the test, because 100 is not a very likely parent population for a sample of 106. So it's consistent with the results of the t-test. Confidence interval and effect size tell us about the magnitude of the effect. It tells us a little bit more information besides whether or not it's just probable or not, because that's what significance testing does. The t-test tells us, well, how likely, how probable is the test given the population, or how likely is this sample given the population. This tells us a little bit more about the size, not necessarily, I'm trying to get really away from the word like importance, but it gives you more the idea of the magnitude of the effect that's sort of separate from the probability. So what else can we conclude from the confidence interval? Like I said before, the neither interval includes 100. You can also conclude, if you were to do the test over and over again, assuming the 106 is sort of a representation of what the samples would look like. If you do the test over and over again, those values are the likely values you would get from samples over and over again as you take them from the same population. So it gives you a bit more information about what to expect in terms of the range of values given that people are taking IQ+. So before, we were able to figure out, based on 100, what do the normal range of samples look like. This is giving you what would the range of samples look like given that IQ+ is working and actually changing people's scores.